Hey guys, welcome back to this dynamics video series. This is the second video on polar problems. This video is going to cover polar problems that do require free body diagrams. Like always, you won't know if you need a free body diagram on your exam or not. So it's important to recognize the first step is, do we need a free body diagram? Well, I guess in our case, the first step is to actually read the problem. The black bent bar is rotating about a stationary vertical axis. So this vertical axis, right? So just up here, it's rotating. Right? And the 4 kilogram red blob can slide on this black bar. All right, there's no friction between the red and the black, and the coefficient, oh no, there is friction, sorry. There is friction between the red and the black, and the coefficients are 0.3 and 0.4. This beta angle equals 30 degrees, right? And this D distance is 0.1, right, meters. So viewed from the top, or this top view right here, the red blob appears to be moving in a circle. And it's asking us what the maximum angular velocity that can be applied before the red blob starts to slide outwards. Okay, so do we need a free body diagram to solve this problem? Ask ourselves, right? Is it a dead giveaway? Is it asking for a force? The question is asking for the maximum angular velocity. So no, not a force. So we don't need a force to solve this, or we don't need. We're not looking for a force, is what I mean to say. So that's not a dead giveaway that we need a free body diagram yet. But we can look for other stuff. So what is our degrees of freedom, right? So if you imagine that we, what's it called? Lock this red thing in place, right? So it's locked in, or stop it from moving, right? Is anything else of interest really happening? No. Right, so if that's it, then we only gonna have 1 degree of freedom, right? So 1 DOF. And just based off of that, we have 1 degree of freedom, right? But we have no velocities given to us, so we can't solve for a velocity without another velocity given. So we have nothing given essentially, and we're gonna need to draw a free body diagram in this case. So let's do it. I'm gonna draw and pretend this is the black line, right? Or the metal bar that the red blob is resting on, just to keep my axis in place. And then my red blob will be right here. Let me get out of that mode. My red blob will be right here. It can be a circle. All right. So what forces are acting on this thing? First is always action at a distance forces. So it's stuff like gravity. So let's draw gravity, right? So gravity is going downwards always, just perpendicular to the horizontal. And it's go to the magnitude of mg. And then we have another force, which is this contact force, right? Or this normal force between the bar and the red blob. And that's going to be going perpendicular to the bar. So that makes a 90-degree angle here. And then we have one last one, which is that we do have friction, right? So in which direction should friction be, right? So what the question is asking us is that if it starts to slide off the maximum angular velocity, right, it's going to start to slide. In which direction will this thing be moving, right? If it starts to slide off, right, it's going to be moving outwards because it's spinning, right? And that centrifugal force is going to just send it out. So how we represent that is the friction is going to be pointing inwards towards this, right? So mu, let's go, Sn, right? Because for now it's stuck in place, and we've got to figure out with what angular velocity we're going to be using to negate that frictional force. Oh, we did forget to label that mu k is 0.3 and mu s is 0.4. But you guys should be aware of that by now, that the bigger one is always the static coefficient and the smaller one is the kinetic. The reason we're using the static coefficient in this case is because the red blob is not yet moving, right? It's just stuck there. And we want to figure out with what velocity we can get it to start moving, right? So we need to overcome that static friction, essentially. Okay, so let's sum forces, right? But before we do that, we got to figure out our axes, right? So this whole thing, we're doing radial and transverse directions. So let's figure out our radial direction. So you're tempted to think that the radial direction is coming out here out of the bar. That looks like this on the free body diagram, right? You're tempted to assume that for your radial direction. But we have to look at the path that we're actually moving on, right? So if you look at it from this top view, this path, right, it's a circle, and that's a circle we're moving on, but it is actually not, oh, let me put this back. It is not moving like this, right, or around this kind of pivot point. It's moving the red blob if we go around like this, right? Because that's the height that it's moving around. So the radial direction, right, is always going to be coming out from the center of this circle, right? I guess the center would be over here, straight out. Our radial direction would be going out this way. So this is our radial direction, right? So we represent this by putting our radial direction along the horizontal, right? So our actual radial direction is not this one up here, but this direction right over here, right? And if you look at this, if we want to find our transverse direction, it's just in the direction of motion, right? It'll be here, or direction of a positive angle change, right? It's actually only visible from the top, right? So we have to look at our top view, right? And it's in that direction. So N theta, right? If you're trying to figure it out on this free body diagram, it's like going into the page somehow. So it's hard to think about, but you can see it if you're looking at it from this top angle. So is that really going to help us? Is that radial direction, or that radial and the transverse direction together going to be what helps us solve it here? Not really, because it's orthogonal. Well, the transverse direction is orthogonal to all of our what's it called forces and all of our the other radial direction. So it's not gonna be much help. But what we can do is we can create a perpendicular, right here, and just label it something like z, right? Or this is z-axis that we're going to be using to sum forces, right? And now we have two perpendicular axes that we can sum forces on. And if you notice, the z-axis is just like any other y-axis when we're doing linear motion. So let's sum the forces. So sum of forces, and let's do the z first, right? So if you remember, just from summing forces from this last exam, we have to sum everything that has a component in this z direction. And that's going to be all of our forces. So the first one is the normal. So we're going to do a normal. And then we have to figure out what this interior angle is. If you remember, just how to get those. If this one is 30, then this angle will also be 30. So we can just say 30. And then if we want to get to the z component, it'll be the cosine. So normal cosine of 30. And then minus, right? Putting minus here because our friction is going against the z. So mu k, or mu s, sorry, mu s n. And then this one will be, if we look at our angles, if you imagine this angle to be 30, then this will be the sine. Wait, is it sine? Yes, it's the sine. It's because it's this one that goes up and down. The sine of 30. And then minus just the full component of mg. And that's going to be equal to 0, right? Because based on our problem, this is all happening before this thing starts slipping or starts moving. So we have no motion, no acceleration, no velocity at this point, right? So this can be equal to 0. And then we can continue on, right? So let's sum now our forces in the NR direction. It's a funny way to write it, but in the radial direction, right? I'm just gonna erase this so it's a little more explicit. In the radial direction, so this is the sum of my forces, and that's gonna be we do still have that n component. So since up there was what's it called, cosine, we're gonna change that to sine. So sine of 30, and then is it going with or against the radial direction? It's going against, right? It's going in this direction, that component. So it's going to be a minus sign there. And then our next one is going to be also that friction. So what's it called? Mu s, that normal. And then since the one above was the sine, this other one is going to be the cosine of 30. And that's going to be equal to two things. That's going to be equal to our mass times r double dot, right, minus r theta squared, r dot theta squared. So how do we get that? If you guys remember from your cover sheet, let me pull it up on my end. You are given this equation, right, for the, let's go, for the acceleration in the radial direction, right? So for polar, if we're looking at acceleration of polar coordinates, it's equal to, from your cover page, r double dot minus r theta dot squared, and that's for anything that's in the radial, right? And then plus r 2r dot theta dot plus r and then theta double dot, and that's in the transverse, right? Since our component of acceleration, or what we're talking about here, is in the radial direction, we're just going to use this radial component to solve this problem. So that's going to be our acceleration and what we're going to use on this side. Our next step is to actually solve these equations. So let's figure out how many known variables and how many unknown variables we have, right? So normal is unknown. Mu s is known, right? So I'm not going to underline it. M is known, G is known, right? So these are all known. R double dot is not known, right? But can we figure it out, right? It wasn't explicitly given, but based on our problem, right? Our R is this distance, right, from the center point. So if that's unchanging, right, because we're talking about before this thing starts slipping, then the change, the velocity or the change in that R distance is 0, right? So the R dot term is 0. And if our R dot term is 0, then our R double dot term is also 0. 0 is just a constant, right? So because this R is equivalent to some value, right, before it starts moving, constant value, then the R dot term and R double dot term are both equal to 0 before we start moving. So this kind of whole problem hinges on that we haven't started moving yet, right? So our dot term is also known. We can just assume that to be 0. And then R is given. And then theta dot is what we're looking for. So we have two equations with two variables, right? Because we're only missing theta dot and n, and we can actually solve it now. Okay, so let me rewrite it. Just include everything we already know. So our equation 1 is going to be that n cosinus of 30 minus, and then our mu s is 0.4 cosine of 30 minus mg, which our mass was given to be 4 kilograms. Oh, I'm not going to write kilogram. 4 kilograms times gravity, so 9.8, and that's equal to 0. And then we can actually solve for the normal force from this equation. So our normal force is just the same as, let me pull in a calculator. I forgot to write an n term, so my math was coming out weird, but I fixed it. So our normal force comes out to be 58.59. Right? And then let's continue with that second equation. All right, so we can actually just start writing stuff in. So negative 58.59 sine of 30 minus 0.4 and then 8.59 cosine of 30 equals, our mass was 4, and then times our double dot, which we said was 0, right? So 0 value there, minus our R value. Our R value, right? We're given a D value over here. So that's this, what's it called? Distance right here from this point to this point, right? So if we want to find this value right here, this R, right, from here to here, we have to do the cosine of this beta angle, so cosine of 30. So it's just d cosine of 30. Now d was given as 0.1, so we're just going to do minus 0.1 cosine of 30. Okay, and then that is all times theta dot squared, right? And theta dot squared is what we're solving for, so I'm going to just put it there, theta dot squared. And then now we have this last equation. We can plug this into our solver, into a calculator. We can solve for r theta dot. So let's see what that is. So theta dot is equivalent to 3.83 rad per sec. And that's the solution to this problem. Okay, so this is going to be our next problem. Let's quickly read it. So everything is smooth. The color B has a mass of 2 kgs. The rod OA is rotating at a constant rate. Just pause real quick. Constant rate, what does that tell us, right? Constant rate, before you even keep going, that's going to tell us that our theta double dot, if it's rotating at a constant rate, is going to be equal to 0. So just point that out initially. Make sure you can spot those things really fast. And the angle theta is 30 degrees, so let's write that down. Equals 30 degrees. And the blue curved rod is in the vertical plane, right? So we have gravity acting down on it. And the absolute value of the acute or small angle between the tangent of the blue rod and the straight rod OA at that point is 75 degrees. So what does that mean? That if we draw a tangent line here to this blue rod, right? And then the small angle between that blue rod and this rod, this small angle is 75 degrees. Okay. And then we have to determine the force the blue rod exerts on the collar. All right, so let's think about this. Do we need a free body diagram? You should get this really fast. Yes, it's a dead giveaway. It's asking for a force, so we definitely need a free body diagram. What I'm going to do is to make this a little less confusing and you guys can see what angles I'm talking about. I'm going to draw it on the actual, on this actual unit, right? So I'm going to make all this stuff a little bigger so I can draw it a little better. We just have to remember that this angle is 75 degrees. Okay. So let's do it. So let's start drawing our free body diagram. So what's the first thing is an action at a distance, right? So it said it's in the vertical plane, so gravity is definitely acting on this. So I'm going to draw gravity going straight down here, and that's mg. What else do we have? We have the normal force, right? Or the contact forces from these collars, right? So the one that's normal to this blue rod is going to be going this way, or perpendicular to the blue rod, and that's the normal of the blue. I think that's actually what we're looking for. Yeah, the blue rod exerts on collar B. And then we have another one, which is the normal force of this actual rod that this collar is sitting on, right? So that's going to go perpendicular to this brownish collar, right? And that's the normal of the B. Brown and blue are the same letter. We'll just call it R for like a rust color. Sure. So anyway, so I think those are all our forces, and now we can determine our axes. So this is a polar problem, so you guys are aware that we're going to be using theta dots, and all that, and our axis system is going to be the radial and the transverse direction, right? So how do we get our radial? That's the first one we got to find out. So it's just from our pivot point or from our center straight out. So let's just go straight out. It's going to come straight out of this bar, and in this direction is the radial. Right. And then our transverse direction is always 90 degrees of the radial, and it's in the direction that we're theta is increasing, right? So our theta, or this angle, that's equal to 30. I got slide a little bit. That's equal to 30 is getting bigger this way, right? So our transverse direction is going to be in that direction, 90 degrees to this, right? It's actually going to be collinear with this normal in the R. Oh, how do I do this without dragging the whole thing? To this normal R force, right? We can just do this. And that's 90. So this is the transverse direction. Okay, perfect. So we summed our forces. We drew our free body diagram. Now let's sum our forces. So a quick summation in the radial direction, right? So sum of the forces in this radial direction, right? That's going to be our NC, right? Or not NC, our NB. So this one. We have to kind of figure out what this angle right here would be, right? So we know that if we draw this tangent line, right, that this angle is 75, right? And since we know that this tangent line and this NB line have to make 90 degrees, because that's what the definition of the normal direction is, right? The normal direction is perpendicular to the tangent of the blue line or the blue bar. Then we can just figure out this angle by doing 90 minus 75, and it's going to be 15 degrees, right? So that's 15 degrees, and then in our NR direction, that is going to be a cosine, right? So let's write that down. So our NB cosine of 15. And then what else do we have in this? We have gravity. Gravity is going to be similar, right? So if we imagine this, this angle right here, or this angle, what would those be? Okay, so if we make this triangle, since this angle is 30, this angle right here is going to be 60, right? So this larger angle. And then since, it's easier than I thought. So we're not actually looking at this dotted line. We're looking at this one, right? Because it's or better color, this one. Because we're talking about the NR direction. It's just going to be the, what is this? The cosine? Or the sine of 60? Yeah, it's the cosine, because it's the angle, the side next to the angle, right? So that's moving in the opposite direction. So it's going to be minus the mg sine of, not sine, I just said cosine. Cosine of 60. And that's going to equal to our mass times our acceleration in the r. Our acceleration in the r, if you guys remember, based on these polar equations, is just going to be, what is it? R double dot, r, and then r theta dot squared. Our acceleration in our radial direction. All right, and now let's sum our other forces. So sum of forces still. Oh, I guess I can only write it once. Sum of forces, but now we're doing in the transverse direction. So in the transverse direction, we still have that NB component, but since we did it sine or cosine in the top, we're going to do it sine now. So sine of 15 degrees. And then what else is in this? We have the entire NR component, so let's just do plus NR. Okay. Did I do it with capital R? Yeah, capital R. And then we also have a portion of the gravity. So since this one was, the top one was cosine, now it's going to be mg sine of 60. And that's going to be equal to our mass again, but this time we're going to do our acceleration in the transverse component. It's just the other side of that acceleration equation, and in the transverse component, I think it's equal to 2r dot theta dot plus r theta double dot, right? Just right off the bat, if you guys remember from the beginning, our theta double dot, since this thing is moving at a constant angular velocity, is going to be 0. So this term cancels. So this entire side cancels. And then we can keep working and figure out what variables we're missing, right? So we need to find MB. That's what we're looking for. We also don't know NR. And we know the angular velocity. It was given from the problem. I think it's, 3 right there at the bottom. So this is fine, and then we know our r currently, or we can find it based on our angle, and then we can also find our r dot and our r double dot just also based on taking the time derivative and using the chain rule, right? Actually, to find those, I'm going to switch over to Mathematica, so let's see. So we know our r is equal to this equation, so 0.2 times 1 plus the cosine of theta. All right, and let's go ahead and switch over and find our r dot and our r double dot. Okay, welcome back to the Mathematica side. So this is going to be similar to the one we did in the last video. We're just going to solve our derivatives for r and then plug in our values. So let's figure this out so that we know. Let's establish first thing that theta is a function of time, right? So just the first thing we can do here. And then r is going to be equal to, and then just directly from our problem, 0.2 times 1 plus the cosine of theta as a function of t, and then this is in degrees, right? So degree. All right, and and close that parentheses. Bang. Looks good. Oh, wait. No, not quite. We gotta close this. And then that'll do it. There we go. Or actually, I'm being silly. We can just leave it as t, because then we're going to input our value later. Okay. Not yet. There we go. Close that out. Okay, perfect. So this is our equation. And now we can get our dot just by doing the derivative of this r with respect to t. And that's going to become that. Perfect. So then let's do our next one. So our double dot is going to be the next derivative, or just equals d of r dot with respect to t. Now let's see what that gives us. All right, so this is our r dot, and our r double dot equations. And then if we want to figure out what these values are, we can start plugging stuff in. So we know that r is equal to, or not r, that theta as a function of t is equal to, and then we were given that it was 30 degrees, so 30 degree, and then our theta dot is equivalent to 3 radians per second, so just 3, and then our theta, since this thing is moving at a constant angular velocity, our theta dot double dot is going to be equal to 0, and that's all. So let's run that, let it run it. And then now we can call all these functions and get our, not these functions, these variables, and get all of our values. All right. And these are our expected numbers. So I'm going to write these down and bring them back over to the math portion. Okay, got them written all down. Now we can plug these values into these equations. So let's do that. So that first equation, right, up top, NB is what we're looking for, and then that times the cosine of 15 minus M, which was given as, where was it? 2 kilograms, so 2 times gravity, which is 9.8, times the cosine of 60 equals 2 times, and then our R double dot, which was negative 1.55, minus R, which was 0.375 or 373, and then our theta dot squared, and our theta dot was given as 3. Okay, and then with this we can solve for NB. So our NB is going to be equivalent to, let me just plug this into a calculator. Calculator gave me negative 0.03. That doesn't look like a point, negative 0.03. Oh, and that's actually our answer. We can still go one step further and solve for NR, which is what I'll do here just to show you guys how we can continue. But that would be your answer for this problem. But let's go ahead and finish it up. So in our second equation, we're going to write down what we have next. So we have NB, which we figured out was negative 0.03. That times the sine of 15. Let me get this in here. Sine of 15. Plus NR minus mg sine of 60. So m is 2, so minus 2. 9.8 is g, and then the sine of 60. And that's going to be equal to our mass, which is 2 again, times, and then 2 times r dot times theta dot. So 2 times r dot, we figured out that r dot based on our thing was negative 0.3, and then our theta dot was given as 3. Right? And then this is plus r times theta dot. Theta double dot, but we already said theta double dot was 0, so we're just going to ignore this term. We don't need it. And then we can now, this is just one equation, one variable. We can solve for NR. Let me plug it into a calculator real quick. And I'm getting 13.4. So that's our second answer if, let's say, the question was asking for the NR. So those are our two answers for this. Just remember with these problems, you gotta make sure you're drawing your axis correctly. So the right radial direction, the right transverse direction, summing your forces right, just like we've been doing, and then make sure you take these derivatives correctly. I recommend, again, just using Mathematica on your exam. It's the easiest way to do it, especially on your homeworks and exams. But that's it. That's all for the video, and see you.